Okay, hello everybody. This is the mock question about the steam pipe and the heat transmitted between it. So I've drawn a picture in Creo. So this is the steel pipe from the mock question. This is the plastic composite, the red, and this is the outer layer of felt, so we can visualize what's happening. And steam is flowing through the middle, and eventually the heat's coming out, transmitted through the steel, through the plastic, and then through the felt to the outside. Now the mock question says that it says here that the steam is at 200 degrees and the outside temperature is 20 degrees C, and it gives us all the dimensions there. So first job is to calculate the thermal resistances, but just before that, just a quick look at where we use steam. We use it in power stations and stuff like that, but one of the other uses in New York, they have steam actually ported around the city, just like electricity. So you can choose to have steam into your building to use it for different things like heating, and you pay for it just like you would electricity. And obviously this needs quite a lot of insulating. Quite an interesting article on Wikipedia if you're interested. Now, as regard the question, let's go through how we're going to do that. First bit, sorry that it's not scanned in very well, but the first part is to work out all the thermal resistances. Now there are actually 5 thermal resistances, even though there are 3 materials. The first thermal resistance is actually the thermal resistance between the steam film and the steel. So if we look back at the picture, so between the steam coming through here and the actual steel pipe work. So the way we do that is we use the heat transfer coefficient, which we see from the question was 500, and then we work out the area of the inside of the pipe for a unit length. So the formula for working out the heat resistance, thermal resistance for this, is 1 over H times A. So 1 over H, which is 500. Now that's the temperature transfer coefficient between steam at 200 degrees and steel. If the steam was at a different temperature or in a different state, it would be different. So remember, this is just a characteristic of that steam at that temperature with that steel and that surface finish. Then multiply this by pi times diameter times 1, which is 1 meter length, and pi times diameter is circumference. Circumference times length is the internal area. Multiply them together and we get 5.68 times 10 to the minus 3. I'm not putting the units there, you've got to work that out for yourself what that is. So that's the first thermal resistance. The next thermal resistance is of the steel pipe itself. And the formula for that we've used in class already, which is the natural log of R2 over R1 all over 2 times pi times K, with K being the thermal conductivity, which is the inverse of thermal resistance, R2 being the outside radius, R1 being the inside radius, and we see the natural log of 0.06, that's the 120 mil diameter outside of the pipe, over 0.56, which is the internal diameter radius, and then 2 times pi times K, which in this case is 45, because steel transmits fairly well. And that gives us a resistance of 244 times 10 to the minus 6. Move on to the plastic, we do the same calculation, except we use the outer diameter of the steel as the inner diameter of the plastic, then the outer diameter of the plastic, and the K value for plastic is 0.2, and we get a value of 0.374. Again, units you'll have to look up. Same units as before though. Do the same calculation for the felt with the outside diameter and the inside diameter, and the K value for the felt is 0.05. That gives us a thermal resistance of 0.462. And then finally, there's a a boundary layer between the felt and the air, so a temperature coefficient between the two, and we do it the same as we did with the steam film on the outside and the inside. This is the air film on the outside, so same formula as before, 1 over h times A, and this time h is 15. Now this is unique to air at 20 degrees and that type of felt with that surface finish. Multiply it by the external area of the pipe for 1 meter length, and we get this R value for the outer air film. Now the next part is to work out the total thermal resistance, which is part A, and that is RT, and we just add up all of the thermal resistances we've just calculated. This is just the same way that you'd work out a series resistive circuit for electrical, that they add together. And if we think about that analogy, the resistors here add together to make the total resistance. The temperatures would be similar to the voltage, and the power, the energy, is going to be similar to the current. And we'll see that analogy work through in a second. So the next thing is the actual heat energy, and the equation for that is Q, which is energy, equals delta T, the change in temperature, over RT, the total thermal resistance we've just calculated up here. 200 minus 20 over the total thermal resistance gives us a total energy of 191.99, whatever the units are. I'm going to let you work that out for yourselves. Next question is to work out what the surface temperature is of the pipe. Now it's not at 20 degrees because that's the air temperature, so the formula we're going to use here is energy, heat energy, is equal to the surface temperature minus the external temperature. Well, the external temperature is 20 degrees, we already know that. The surface temperature is what we're looking for. The thermal resistivity of the steam film we calculated up here, 0.0956. And energy, we talked about that being like current, so it's 191, because current in a series circuit stays the same throughout, and energy, it can't disappear, so it's got to be the same throughout the whole pipe. So here is the equation rearranged. Q times R of the air film plus the external temperature equals the surface temperature. We plug those values in. The energy, the thermal resistance of the air film, plus the 20 degrees of the external temperature gives us an external temperature of the pipe, if you were to touch it, of 21.84 degrees, showing that this pipe really does insulate quite well because it's only 1.84 degrees above the surroundings.